Today, we're reasoning through the impact of air pressure and temperature on aircraft performance and airport design without hesitation, repetition, or deviation starting now. Air pressure and temperature significantly affect aircraft performance and in turn have a profound influence on airport design, particularly in determining runway length and airfield layout. Air pressure is a critical factor in determining air density. As pressure decreases, fewer air molecules are available in a given volume, leading to lower air density. When the air is less dense, aircraft need to achieve higher speeds to generate sufficient lift, which translates into longer takeoff runs. For airports located at higher altitudes where atmospheric pressure is naturally lower, this effect becomes particularly important. For instance, at sea level, the standard air pressure is 29.92 inches of mercury, and as altitude increases, air pressure decreases. At an altitude of 5,000 feet, the standard pressure is only 24.9 inches of mercury. The reduction in pressure at higher altitudes effectively increases the pressure altitude, which mimics the conditions of an even higher altitude. Aircraft taking off from such locations must cover longer distances on the runway to reach the airspeed necessary to compensate for the thinner air. Temperature also plays a significant role in determining air density. As the temperature rises, the air molecules move more rapidly and spread further apart, reducing air density. The combination of high temperature and low air density, common in warmer climates and high altitude locations, creates a condition known as density altitude, a measure that reflects the combined effects of air pressure and temperature on aircraft performance. In higher temperature conditions, an aircraft may struggle to achieve the same level of lift that would be possible at lower temperatures, even at the same altitude. For example, at 10,000 feet, the standard temperature is 23.3 degrees Fahrenheit, while at 5,000 feet, it is 41.2 degrees Fahrenheit. If the actual temperature is higher than the standard, the air density decreases further, effectively increasing the density altitude. This requires even longer runways to compensate for the reduced performance. Airports located in high altitude areas or in regions with frequently high temperatures must be designed with longer runways to allow aircraft to reach the necessary airspeed to take off safely. For instance, airports like Denver International, located at 5,434 feet above sea level, have much longer runways than airports at sea level. This is because at such high elevations, lower air pressure makes it harder for aircraft to generate lift, so they require more runway distance to achieve takeoff speed. Similarly, airports in regions with extreme temperatures, such as in the Middle East, must account for the effects of heat on air density. On hot days when temperatures rise significantly above the standard sea level temperature of 59 degrees Fahrenheit, air density drops and aircraft require longer distances to achieve takeoff. In these cases, airport designers must extend runway lengths to ensure aircraft can safely take off in high temperature conditions. To standardize how these variables affect aircraft performance, the International Civil Aviation Organization, or ICAO, has defined a standard atmosphere. This assumes that air pressure at sea level is 29.92 inches of mercury and the temperature is 59 degrees Fahrenheit. Based on this, standard atmospheric conditions are calculated across different altitudes. It assumes that with altitude, both pressure and temperature decrease. When the actual pressure or temperature deviates from the standard, airport planners and pilots must adjust for density altitude. For example, at 5,000 feet, the standard pressure is 24.9 inches of mercury and the temperature is 41.2 degrees Fahrenheit. If the actual conditions show a lower pressure or higher temperature, the density altitude will increase, meaning that the aircraft performs as though it were at a higher altitude than the actual elevation. This could significantly affect takeoff performance, as lower density means less lift and thus longer required runway lengths. When the barometric pressure drops below the standard 29.92 inches of mercury, the air density decreases and the pressure altitude increases, which essentially mimics the effects of being at a higher elevation. For example, if the pressure drops to 28.86 inches of mercury at sea level, the aircraft will behave as though it were taking off from an altitude of 1,000 feet. This reduction in air density due to lower pressure results in a longer takeoff roll, requiring airports to adjust runway lengths accordingly. Conversely, higher than standard pressure results in higher air density, which improves aircraft performance and reduces the required runway length. This must be taken into consideration while undertaking construction for a new airport. In conclusion, air pressure and temperature play crucial roles in determining the air density, which directly impacts aircraft performance. To ensure safe and efficient operations, airport designers must account for these variables, especially in high altitude and hot weather locations. By understanding the effects of air density, pressure altitude, and density altitude, airports can be designed with appropriate runway lengths and infrastructure to support optimal aircraft performance. If you like this video, don't forget to hit the like button, leave your thoughts in the comments, and subscribe for more aviation content.